And we're looking at chemical kinetics. Kinetics, let's see, before we get into the meat of kinetics, what is kinetics? In physics, can be broken into two sections. Either statics, where nothing's moving. Everything is, there's a balance, but there's no motion. And kinetics implies motion, movement of some kind. So in this case, the movement is how fast is the reaction rate proceeding. That's our focus for this chapter. And that's why we reference kinetic energy so often. The kinetic energy of a particle is 1/2 mass times velocity squared. But it's not quite that simple with chemical reactions because you've got so many players. Sometimes you only have one in a decomposition, for instance, but very often you have two players as reactants, in which case you could have possibly a replacement reaction or displacement reaction or a double displacement reaction, for instance. We're going to start off simple, right? And we're defining the reaction rate. By the way, if you've looked ahead in your textbook, you'll see that equilibrium is, I think it follows. I believe it follows. Yeah. Equilibrium follows kinetics for a reason. Now, historically speaking, equilibrium was identified and quantified earlier than kinetics. But when it comes to understanding how equilibrium is established, we need kinetics to get a full understanding. So we're going to do kinetics first. And when we describe a chemical reaction, you can describe it in several ways. If you have say A plus B yields C plus D, then you can say, how fast does A disappear? Or how fast does B disappear? Or how fast does C appear and D appear? We find it's easier to describe a chemical reaction if we approach it from this side, and we approach it from the very beginning, before you have any C and D. Because what we've learned is that once you get some C and D over here, you can get a reverse reaction. So we start under initial conditions. And we're going to focus on just one of the reactants for now. We could even eliminate this one for simplicity's sake. So what we're going to say is a change in concentration, and we use square brackets to represent concentration. So the concentration of A at any time T1, which could happen anytime during a reaction, but like I said before, we prefer to start. So what we want is a change in concentration. That's what the delta means. Over a certain period of time. And time could be anything. Depending on the reaction, it could be hours, days, years, seconds. Some reactions happen so fast, milliseconds and microseconds are the time intervals. So we want to determine the change in concentration over a change in time. And whenever we say delta, a change in chemistry, well, actually in physics too, we say, what are the conditions at the end? right? Concentration at time 2 minus the concentration at time 1. So then we get T2 minus T1. And notice that if we're starting at the beginning, concentration of A is higher than it is at the second time. So that means our value is going to be negative. That would give us a negative change for, so the sign tells us that we're losing A over a period of time. And typically the units of measure for this concentration is molarity or moles per liter, unless some other unit is specified. Okay, so in this table, which comes straight out of your textbook, we have a set of data. Now, in this case, this particular reaction, nitrogen dioxide decomposes into nitrogen monoxide and oxygen at an elevated temperature, actually. And what we've been able to do, probably through spectroscopic means, is watch the concentration change for each of these gases. So at time 0, we have only nitrogen dioxide and no nitrogen monoxide or oxygen. That's the initial condition. And then after 50 seconds, we find that we've lost some nitrogen dioxide, and now we have some nitrogen monoxide and oxygen. Well, notice, what did we lose? 0.01 for nitrogen dioxide at it's T0 and 50 seconds. We just look at the first step to get an idea of what's happening. And this is nitrogen monoxide and oxygen. And these are molarities. So this is 0.01 molar, 0. Then after the first step, we have 0.0079. And we've created 0.0021 molar and 0.0011 molar. Okay, after those first two. Well, if we use our definition from the previous slide, we find that the difference between this one and this one is what? Well, actually, it's that one, right? Final minus initial. So this would be a change of minus 0.0021 molar. Look at the balanced equation. Let's see. 2NO, and these are gases, of course, yields NO plus O2. Okay. So notice that the ratio is 1 to 1. So if we lose 0.0021 molar from here, it should show up over there. And it does. But we only have half as much oxygen, and it's 0.0011. So the stoichiometry is obeyed in this data set. And after another 50 seconds, we find that we've lost what? 7965 is 14 or 0.0014. Well, 0.0014 and 21 is 35. Right? And that's what we have. We've lost that much more, so it shows up on this side. So the point of this slide is, well, one point is that stoichiometry is not thrown out so we can study kinetics. Stoichiometry is still there. And we notice as we proceed, actually, the same time interval, we've gone another 50, so we go to 100 now. But the difference between this one and this one, 6.5, the difference here is less than the difference there. So what we're seeing is the reaction is slowing down. It's not linear for this particular reaction. Okay. So here's a graphical representation, and this comes out of your book too. It's kind of hard to see, but if you can see the general trends for the lines. The top line, we're starting at 0.01. And of course, that's nitrogen dioxide, and nitrogen monoxide and oxygen are 0 at the very beginning. And we see as the nitrogen dioxide decreases, the other two increase stoichiometrically. So you should see the nitrogen dioxide curve is mirrored in the nitrogen monoxide curve, and it's half mirrored in the oxygen curve. The other thing to observe about this particular graph is the curves, they're not linear. But if we say, if we take, let's see, time and concentration, okay. If we take this, just take the top curve for illustrating the change in nitrogen dioxide over a period of time is equal to the slope of the straight line that is tangent to the curve at any given time. So if we pick a time down here and we draw a tangent to that, then the slope of this line, rise over run, right? Rise over run, this change here versus this change here, gives us the rate of the reaction at that time. So notice that it changes, right? If we come down here, then the slope is shallower. If we go up here, it's steeper. So that tells us that the rate of the reaction is not linear. I mean, we are calculating the rate at the tangent, but any point on that curve will have a different tangent. And you can do that for the other curves as well. So what we have calculated with this reaction rate is the instantaneous rate of the reaction at any point of time on that curve. All righty. And I've already mentioned that, the instantaneous rate. Okay, now when we describe a chemical reaction, we apply to it what's called a rate law. Now remember, laws, and this follows the same pattern as laws that we learned in the beginning of the first semester. Laws just describe what's happening. They make no attempt at explaining why. So this rate law has proven to be useful for describing the rates of different types of reactions. And they're not all the same. They fall into groups, into categories, but even then they have dissimilarities. So when we describe the rate law, what we're saying is the rate of a chemical reaction and using whatever units of measure we designate for that particular experiment. Is equal to some constant, which we call the rate constant, times the concentration, in this case, NO2 for that reaction, NO2. And this would be, of course, a loss of NO2 over time. And then this is to a power, N. And that power is known as the order of the reactant for that particular react. If we had two reactants, then we would just add a term out here for the second reactant, and it would have a separate order. And we're gonna look at those in just a minute. But this is the simplest form. When you say rate equals something, then it has to have a constant. It has to have concentration of the reactant to a given power. Now, for convenience, we're going to study these values, these powers, either 0, 1, or 2. But as a practical matter, that power can be anything. It doesn't have to be an integer. It's just convenient for us to study it that way to get the most out of this chapter. All right, we're just making a blanket statement here. Notice the concentration of the products don't appear in the rate law because the reaction rate is being studied under conditions where the reverse reaction doesn't contribute to the rate. This is initial conditions, initial rate. That's an initial rate law. And like I said before, we study it under initial conditions because if we allow products to accumulate, that muddies the water, so to speak. It makes it more difficult to draw any conclusions about this particular reaction. Now, as a practical matter, we do incorporate products in other expressions, but for now, we're going to stick with this one. Rate law under initial conditions is that expression for the reaction we've been studying for the past couple of slides. This value N has to be determined experimentally. You cannot derive this one from the balanced equation. Now, if this power, say, is the same number, if you determine by experiment that this power, this order, happens to be the same number as the coefficient in the reaction, it's purely accidental, right? There's no connection at this point, right? When we get to the point where we're going to talk about mechanisms, then we can we'll draw some conclusions there, draw some values from the balanced steps, right? We haven't got there yet. But for now, this has to be experimentally determined. And if we derive that from some other method, then this is one of the checks. Our method, what did I say it was? Mechanism, excuse me. From the mechanism, if we derive a value from the mechanism, then it has to equal that. It can't be anything else. Otherwise, our mechanism is false. Okay. This particular rate law is what's known as the differential. The differential rate law. And it shows the rate of the reaction as it depends upon concentration. Now, these terms are derived from calculus. And if you've had calculus, or if you're going to have calculus and you want to know more about it, then I've got a couple of handouts that are available in Brightspace, right? Otherwise, just memorize it. This is the differential rate law. It can also be, from this, we can derive another rate law expression that shows how the concentrations of each of the species that are in the expression depend on time. Notice that there's no time factor in here. It's just at any point in the reaction, we know this concentration, then that, well, actually, the initial concentration, then we know the rate constant and the order under initial conditions. But we can derive an integrated rate law. The integrated rate law is an expression of concentration versus time. And sometimes that is even more useful. We're going to study these reactions in terms of reactants only, because we're focusing on initial conditions. Now, the data set that we looked at a couple of slides ago incorporated values for the products as well. That was to illustrate the fact that kinetics does not divorce itself from stoichiometry. The derivation of this one into the integrated form, and it's different for each of the orders, right? So that's why I didn't put something up here, because it will change depending on what the order is. But once we do that, then the relationship between the differential and the integrated rate law for any given reaction is well defined. So if you determine the integrated rate law, you can derive the differential rate law from that one, and vice versa. So that gives us a couple of ways to attack a reaction and determine its kinetics. And of course, chemists generally are not stupid, right? We're not going to do things the hard way unless we have to. We do things the simple way, the easy way, the quickest way to get to an answer, as long as the answer is justified. So the experimental convenience dictates whether we're going after this one or that one, how we approach analysis of a chemical reaction. If we determine the overall rate law, right, and this is what I'm going to be referring to as the overall rate law, because most chemical reactions occur in steps. We don't see those steps unless we have some really sophisticated equipment, and we can, on the picosecond scale, we can watch the progress of the reaction, and it's very difficult to do. So we propose individual steps. Most reactions occur with at least 2 steps to get from reactants to products. And those steps constitute what we call a mechanism. So knowing the overall rate law allows us to propose steps. It's kind of a, I don't know, process of elimination. We propose a mechanism with these steps, and then we propose another one, and then we propose another one, whichever, and several of them, actually, sometimes a dozen of them, are possible for any chemical reaction. And then we go through a process of eliminating, right? Which one satisfies the conditions of the overall rate law? Throw them out. If they don't, throw them out. And eventually we get down to a choice of one, hopefully just one, sometimes 2, and then we have to maybe do some more experiments to find out which mechanism is the most probable. we've already said this. The overall rate law has to be determined experimentally. And that order, the power, has to be determined experimentally. So over time, chemists have devised this method called the method of initial rates. And the reason we say rates is because the method requires, depending on the overall chemical reaction as written, the balanced equation, the method of initial rates will have at least 2, maybe 3, 4, or 5 separate experiments, rate experiments, that give us information about each one of the reactants and products. Well, it's usually confined to reactants only because it's initial rates. Okay. At time 0, we watch the rate at the very beginning. So we try to get data as quickly as possible and in sufficient quantity so that we can write the initial rate law without interference from products. All right. It's probably going to make more sense if we just do one. But before we do that, if we have a rate law expression that has more than one reactant in it, in this example, where we say the rate is equal to a rate constant, concentration of one of the reactants, concentration of the other reactants, then referencing the order of the reaction is a summation of the orders of each of the two. So the reaction order is simply a summation of the individual reactant orders. So say if this was, say if that was first order, right? Then we wouldn't write anything up there, right? If you've got 1 there, it has to have a 1 here, first order. And let's say this one happens to be 2. Okay, second order. Then the overall order would be 1 plus 2 equals 3. It's really simple. Okay, just to see if you were paying attention. How do exponents, orders in the rate law compare to coefficients in the balanced equation? And the answer is they are not related. Why is that? Because the balanced equation expresses stoichiometry. It doesn't say anything about how fast the products are produced during the reaction. That topic is covered in mechanisms. And notice that note at the bottom, and I sort of referred to it earlier. The rate law steps in the mechanism can be deduced from the individual steps of the equation. So if I have several steps, then I can write a rate law for that step. And then each step has its own rate law, and the overall rate law has to be a combination of those 3 using certain rules that we'll discuss later. All right, so let me clear the board. We're going to talk about 3 types of rate laws. And this is where we're only discussing a single reactant. The order can either be 0, 1, or 2, right? And there's certain characteristics that are identified for each one of these orders and help us get a grasp on the order of a given reaction. with reference to that reactant under initial conditions. Okay, so the first one is the zero order. And the rate law, the differential rate law for the zero order is simply this, right? Rate constant, and then A to the zero power. So what does that mean? Math, right? Arithmetic, math tells us that anything to the zero order is 1. So the zero order, the rate is simply the rate constant. Okay? When we derive the integrated rate law, we find that the concentration of A at any time that we designate during the reaction is equal to a negative K times T plus the initial concentration. Right? So notice that this is in the form of a straight line. Y equals mx plus b. So that means if we draw this expression where time is x and the concentration of A is y, then we get a straight line with a negative K slope. Okay? So that's how we identify a zero order equation. Okay? We have the concentration of A over time, and we plot those values. And if the plot gives us a straight line from just the raw data, concentration time gives us a slope line with a negative slope, a straight line, we know it's zero order. Okay? And there's our example. Okay, one other thing we can deduce from all this information is the half-life. All right, you may have heard of half-life before in reference to radioactive decay. Well, there's a half-life to chemical reactions also. And the half-life of this reaction, T1/2, is equal to the initial concentration over 2K. And let's see, let's make that K like that. Okay, what does that mean? That means if we know this concentration at any time, and we know the half-life, then we can calculate K. All right. Now, the A0 for the experiment is actually the concentration at time 0. But for using this equation, and actually this equation as well, you can start at any time you want. Anytime becomes your time 0. So what we find is, as the reaction progresses, the concentration of reactants decreases. If we give a value here, and this half-life is constant, so, and this is a constant, so the only variable is A. And it changes, it gets, well, actually, that's not true. That's not true. That's a constant. This is a variable. These are two variables. So that means as this one goes down, this one goes down. So the half-life is variable depending on the initial concentration of A. All right. And there's a derivation of the half-life. You don't have to memorize this. I just put that in there for information. If it doesn't interest you, then don't worry about it. But you do want to memorize that red one at the bottom. Okay, the next possibility is first order. Okay, so first order would be rate of the reaction equals K, and this is a different K. The K depends upon the chemical reaction itself. Each chemical reaction will have a different K. The initial concentration to the first power, and we don't need to write that up there, right? Okay. So that's an expression of the rate law. The integrated rate law is this one. Okay. Oops, sorry. Wrong place. There. Yeah. Excuse me. So what does that mean? This looks like a straight line, but you can't plot A against time. You have to plot the natural log of A. So if we drew the graph for this one, and this is time, this would be the natural log of A. And it would also give us a straight line where the slope is equal negative K. All right. That's what it would look like. So as a practical matter, if you determine values of the reactant over a short interval of time, and you transform the concentrations into their natural logs, right? You have to find out where that key is on your calculator. It's usually Ln. That's natural log. Log is common log, base 10. This is base E, right? It has to be the natural log. But if you do that and then plot these values against time and get a straight line, then you know the overall reaction is first order. All right. If we do a similar derivation for this expression and get the half-life, we find that the half-life is 0.693 divided by K, which means what? Which means the half-life does not depend on concentration. For a first order reaction, the half-life will be a constant, right? That's a constant. That's a constant. So that has to be a constant. So if you plot your data and find this relationship, you know it's first order. Or if you determine the half-life, you measure the half-life at various points in the reaction and they're all the same, then you know it's first order, and you can use this equation to calculate K. And there's the derivation for the first order half-life. Okay, before we go to the second order, we're going to look at this problem. A first order reaction is 35% complete at the end of 55 minutes. What's the value of K? All right. A first order reaction is 35% complete at the end of 55 minutes. So if we do first order and time, then at 0 time, you have a certain value here, X. And then after 55 minutes, what's the value of A? Well, it's 35% complete. So what's left? What's left over is 65%. 35% is gone. So what you have is 0.65 X. Okay. We know it's first order, so we can use this value here. What's the half-life? Well, how long does it take for half of it to be gone? It's only 35% of it gone now, not half. Okay. So if we take the equation here and we solve it for the ratio of A to A0, and that's what I've done here. I've taken this equation and I've reduced it to this form where we get the ratio of A to A0. That's what we want, because the ratio of A to A0, what's left versus what we started with, is 0.65. So 0.65 equals E to the minus KT. Now we can solve for K. And that's what I've done in the rest of this animation. Okay. So there's our ratio, right? A to A0. There's the expression. We just need to reduce that expression to find out what K is, because we can't do that. So once we have this value, then if we take the log, the natural log of both sides, right? The natural log of 0.65 equals the natural log of E to the minus KT, right? And the log base E of E to a power is the power. So that's how we get to that point. If you're not fully conversant with logarithms, then this might twist your head around. But now that we have an equation with, we need to substitute for T, 55 minutes. After 55 minutes, we got this ratio. So we change that to 55. Now we can solve for K. And K is 7.8 times 10 to the minus 3 minutes, reciprocal minutes. So we can put that in here and find out what T1/2 is. Wait a minute, what was the question? Oh, what's the value of K? Right, we don't have, it didn't ask us for the half-life. We could do the half-life. We just take K and put it in here and solve for the half-life. I didn't animate that one though. All right. So the last one we're going to look at is second order. Okay, so the rate equals K A squared. Okay, and the integrated rate law is not the natural log, but the reciprocal. That. So how do we deal with that one? Y equals mx plus b. So if you plot 1 over, or the reciprocal of A against time, you get a straight line now with a positive slope. And the slope equals K. Okay. All right, I'm going to put this all together for you in just a minute. Question is, how do you use what we know here to extract this valuable information from chemical reaction rate data? Oh, I forgot the half-life. Okay, so the half-life of this one is calculated at 1 over K times the initial concentration of A. There you go. Okay. So what this tells us is, as the reaction proceeds, the half-life gets longer, because this is in the denominator. As this increases, this value, let's see. No, as A decreases over time, then this expression gets bigger. That means the half-life is longer. It takes longer for half of the reactant to disappear. And there's the derivation for the second half-life. Okay. Before we get to this exercise, this example, notice that all of these can be based upon a single set of reaction data. And you're trying to find out, is it zero, first order, or second order? Then what you do is set up your table with your raw data against time, like this, against time. Then you would take the natural log of those values against time and the reciprocal of those values against time. And you get, so you plot these data, you plot these data, and you plot these data, 3 separate graphs. Which one is linear? The linear one tells you which one it is, right? These two will be linear with a negative slope, and that one will be linear with a positive slope. So then you can determine what's the overall order for that reactant. One other thing to notice about this data, okay, is look at the half-lives. The half-life here is A0 over 2K. This is 0.693 over K. This is 1 over K times A0. Notice that the half-life is inversely proportional, right? Inversely proportional to K in every instance, because this is in the denominator, denominator, denominator. Now, A fits in there somewhere, but K and T and the half-life are inversely proportional for every one. All right, so let's take a look at this example. Let's see, I've run out of room. Let me erase this one and use this part of the board, since that's the simplest one. So here we have a reaction. A becomes product. The initial concentration of A is 5 molar, and the first 2 half-lives are 25 and 50 minutes. Okay, so let's put this data up here just so that we get an idea. At time 0 and at time 25 minutes, yep. What's the next interval? Well, the next half-life is 50 minutes after that. So 50 plus this, right, 50 minutes here, means that this is 75 minutes. We may not need that, but we do know. This is the first half-life, 25 minutes. Now the concentration of A0, actually A, concentration at time 0 is 5 molar. Okay. Half-life means what? How long does it take for half of the reactant to disappear? So after the first 25 minutes, what do we have? We have 2.5 molar. The next half-life is half of this one, which is 1.25 molar. Okay, so write the rate law for this reaction. Well, the rate law is simply what? Oh, we need to look at the half-lives. Okay. So the rate law for the 0 order, are you done? Okay. Oh. Okay. the half-life for the zero order is, see if I can remember. A over 2K, I believe. That's, yeah, okay. The first thing to note here is the rate law, is the half-life dependent upon concentration? Does it change? As the concentration changes, the half-life changes, 25 to 50. That means it cannot be first order. Because with first order, the half-life does not change with concentration. All right. If the rate law were zero order, then we would have this expression here. All right. And here's your calculation. If you do the zero order calculation at 25 in here, and you substitute 5 molar in here, what's K? K is 0.1. Do the same thing for this half-life. Now we're starting with, we're going 50 minutes, and we're starting with 2.5 rather than 5. So 2.5 goes in here, and here is 50. Okay, so we calculate the K, and it's 0.25. That means it cannot be zero order. Because if it were zero order, that's not right, it should be down here. If it were zero order, then the, well, yeah, if it were zero order, the K would be the same for both. Because the K is a constant. It cannot change. Right? So it can't be zero. It can't be first order. It cannot be zero order. It must be second order. But we got to prove it. Right? So for second order, the half-life is this expression. And we do the same thing. We substitute the initial value and the half-life into the equation and determine the K value. Okay. For the first one, we get K equals 1 divided by 125. And we do the same thing for the second one. We get the same value. 8 times 10 to the minus 3. That means our reaction is second order. All right. And there's our rate law. The rate law is simply the K times the reactant to its order. Now we substitute in there for the K. There you go. And we write the rate law. Wait a minute. Actually, the rate law should be this. Whatever the value for K is, times A to the second power. That's the correct expression for the rate law. Okay, and the other question was, what's the concentration of A after 525 minutes? Well, notice that we've got time in there as a variable. So we have to use an integrated rate law. We have to use this one here. So if we start off with 5 molar here, and we put in 525 minutes here, plus our K in here, 8.0 times 10 to the minus 3, then we calculate A from here. Okay, and that's what I've done in that animation. We solve for A. And after 525 minutes, we should have 0.23 molar A. All right. And there are all our answers in one page. Okay, I mentioned this one earlier. This is in black and white on the slide. So how do you determine which you have? Oops, I'll skip it. How can you tell the difference between zero first, second order rate laws from their graphs? Oh, I already showed you that one. Right. You know that the graphs are going to be a certain slope depending on whether it's raw data, it's the natural log, or it's the inverse of the concentration against time. That gives you an indication of which one it is. If, and this is going to be an abbreviated description. What do you do if you have more than one reactant? Right. Well, we know what the expression looks like. The rate law looks exactly like that. But when we're trying to tease out what is the order for each one of the reactants, what we've devised is a modified version of the reaction in which we increase the concentration of one of them, say B, increase the concentration of B so high that it effectively does not change concentration during the reaction. Okay. So in that case, what you end up with is a pseudo rate constant. That's why we put a prime on it. So if we start off with the rate equals K times A to the N and B to the M, and B is so high that it doesn't change, then K times B, that means B is constant, is equal to a new value there. And the rate equals this K prime times A to the N. And as long as we keep B so high that it doesn't change, then we can investigate it for first, second, or third order. Okay. Once we determine what that is, then we do the experiment again at a different concentration of B. And I'm going to hold that discussion until we talk about the lab, because we're going to use this method in the lab itself to analyze our data. Actually, we're going to use this method in two separate experiments. And because our reaction involves two reactants. One is the dye, right, the food coloring, and the other is bleach. So we hold the bleach high, and we determine the order for the blue dye, and we do it again at a different concentration of bleach, and that allows us to find out what the order is for the bleach. But that'll be a more complete discussion will follow when we talk about the lab. Okay, so here's a summary of everything we've talked about so far in terms of zero first and second order reactions, right there in one table. You probably want to memorize that. Okay, now we have an exercise. Let's see. So this reaction where we have A going to products, we start off with A at 5 molar, like our previous reaction. And K we're given as 1 times 10 to the minus 2. Calculate A after 30 seconds have passed, assuming the reaction is zero order, first order, second order. So if we're going to calculate A over a period of time, that means we need the integrated rate law. So we need the integrated rate law for the zero order, which is this one, A equals minus KT times A initial A. And then we substitute the values in there that we were given, and we find that after 30 seconds, our concentration of A is 4.7 molar. Do the same thing for the first order. Substitute those values, only now it's into a natural log transform. and we calculate the value of A after 30 seconds, we find it's lower, 3.7 molar. So I'm guessing that the second order is going to be even lower, right? 2 molar. So the point of this slide is to illustrate the fact that the order says that for 0 order, the reaction is going at a certain speed. For first order, it's going faster. For second order, it's going even faster. So as the order increases, over a certain period of time, you have less reactant left over. Okay, now for the method of initial rates. I'm going to need the whole board for this one. So for this reaction, we have 2 times MnO4 minus and 5 H2CH2C2O4. I think that's oxalic acid plus 6 hydrogen. And then the products are manganese 2 plus 10 CO2 and 8 water. So we didn't have to balance this one. Notice also that our charges are not balanced. That's not a problem. We know that the manganate ion is going to have a counter cation, maybe like potassium or something like that. But it's a spectator. All right, so we leave it out for convenience. And the same thing for the other ions. These are the reactants of importance. The initial rate data is this. So we have under here, and that's why I like to write out the equation and then put the data under the reactants here. So after, let's see. Okay. So if we have a concentration and we're saying molar, and this is experiment, it doesn't say that, but I'm going to say experiment 1, 2, 3, and 4. Notice that we have to have 4 experiments because in order to use this method for 3 reactants, we have to hold 2 of them constant between 2 experiments. So let's say we have experiment 1 and 2. We see that oxalic acid and protons are constant while we let the manganate ion vary. So we go 1 times 10 to the minus 3, and then the rest of them 2 to the minus 3, 2 times 10 to the minus 3, and 2 times 10 to the minus 3. And then we have 1, 1, 2, 2, and these are all times 10 to the minus 3. Molar. And then the last one we have 1, 1, 1, and 2. So what you'll discover is if you have 3 reactants, you need 4 experiments in order to have the right combination of concentrations. If we only had 2 reactants, then we'd only need 3 experiments. All right. So now we have the initial rate. Right, so the rate for the first one is 2 times 10 to the minus 4, then 8 times 10 to the minus 4. 1.6 times 10 to the minus 3. And 1.6 times 10 to the minus 3. Well, okay, the units are molarity per second. Okay. So here's how you take the rate expression for this equation, which is, oops, okay, I have to do that. So the rate of this expression, of this reaction, is concentration of, is the rate constant, the concentration of manganate ion to the N times oxalic acid, I think that's oxalic acid, to the M, there we go, and then protons to the P. I don't want to use O because we can mistake that for a value. Okay, so how do we deal with this data? Well, what we want to do is set it up so that two of them cancel and we leave one behind. And in order to do that, we need a ratio. So we set it up again, rate equals K like this. So we just ratio these values in this rate expression. And if we do that, then we pick the ones depending on which one we want to keep. So let's say we want to keep this one first. All right. So what we do is we say, what's the rate for, since this one is bigger than that one, I'm going to put this one on top. It really doesn't matter. So the rate at 0 times 10 to the minus 4 ratio to the rate 2 times 10 to the minus 4 is equal to K. And I'm going to do this one complete the first time. Right? This is the same K, top and bottom. And what's the concentration of this? 2 times 10 to the minus 3. And that's to N. And the second one that we put here is, oops, sorry. Yeah, 1 times 10 to the minus 3 to the N. And then these are going to be the same because that's the way we set up our experiment. This one's going to be 1 times 10 to the minus 3. And this one's 1 times 10 to the minus 3. And this one is 1 and 1. So notice what happens. Oh, I forgot M and P. N and P. Well, this expression is exactly the same as that one, cancels out. That one cancels out, that one cancels out. This cancels here. So if we reduce this expression, what's 8 divided by 2? It's 4, correct? Okay. What's this divided by this? Well, notice that when you have A to the N divided by B to the N is the same as A divided by B, both to the N power, right? This N comes out. You can, I forget the proper math term, but you can combine them. And 2 divided by 1 is 2 to the N power. So N must be 2. 2 squared is 4. That's how we determine this one here is 2. Okay. And then you pick the next reaction where you have MnO4 the same in both cases, like this one, and we let this one vary from 1 to 2. This one's the same, that was the same. We do the same thing here. We get 1.6 divided by 8 actually 16 to the minus 4 divided by 8 is 2. And we run through that whole procedure again, canceling everything except this expression. And then it equates to this ratio, and we say what power will give us that answer. And we do that for each one. And what we find is, let's see. Well, that's jumping ahead. Hold on a second. What we find is that this one is second order, this one's first order, this one's 0 order. We just do that same procedure for each one. So now that we have this expression, we know all the orders, and we want to find out what K actually is. So we just pick one up, right? It doesn't matter which one, right? We could pick, let's pick the first one, right? The rate is 2 times 10 to the minus 4. And that's equal to the concentration of MnO4, K times 1 times 10 to the minus 3 to the second power. And then the next one, 1 times 10 to the minus 3 to the first power. And then what is this one? Well, it's 1 to the 0 power, but it doesn't matter, right? Anything to the 0 power is 1. So what do we get? Well, we get 1 here. We get 1 times 10 to the minus 3 here. And we get 1 squared. So it's 1 times 10 to the minus 3 squared. Should be 1 times 10 to the minus 6. No, it's not. Hold on a second. 1 exponent 3, enter, and square it. There we go. I was right the first one. 1 times 10 to the minus 6 is K, and that's equal to 2 times 10 to the minus 4. So we say this one times this one, take that over here and divide it into that one. That gives us K. And K is 2 times 10 to the minus 5. So our expression is, here we go. This then becomes 2 times 10 to the minus 5 times MnO4 minus to the second power, H2C2O4 to the first power, and hydrogen ions aren't there, right? Because it's 0 power, they're gone. Now, how do we know what to do with that? Well, here's the expression for the reaction. We know that if it's not in the final, if it's not in the rate law, that means this one must be 0. Okay, so there's your rate law, and that's the method of initial rates. All right. Stop me if you have questions. There's several of these in the review document. Give you some practice. We'll look at those next week when we do a review. Okay. Now let's talk about reaction mechanisms. Like I said before, most chemical reactions occur with at least 2 elementary steps that we don't see. We see reactants, we see products, we don't see any type of underlying steps that they through which they proceed. But we know it's there from other investigations. What forms in the process of an elementary step is called an intermediate. And the intermediate, since the intermediate is not part of the products, then any intermediate that forms in a step must be consumed in a subsequent step. It cannot appear as a product if it's an intermediate. If it's a product, yeah, it'll stick around. It may react further, but you still have to have that product in the overall reaction. So here's an example. If we have NO2 plus carbon monoxide, carbon monoxide, and it reacts to form nitrogen monoxide plus CO2, this is the mechanism for that reaction. In the first step, we take two of these, and they react to form NO3. So we have step one. We have two of these NO2s react to form NO3 plus NO. Well, there's a product right there. Now, do we keep it? Well, let's see. The second step, we take this NO3 and react it with the CO. And that gives us that gives us NO2 plus CO2. There we go. Okay, notice that we had to react two NO2s here to get to this step. But we used up, or this side balances that side to the effect of one of these. So that means one of these cancels out and leaves us with NO2. So that these two together account for that one. This one's an intermediate, right? So it cancels. It appears and then disappears. This one is a reactant, right? So it's good. This one is a product, so it's good. And that one's a product. So we have one of these left, right? Plus one of these yields one of these plus one of those. Okay? That's one of the conditions of a proposed mechanism for a reaction. You have to be able to add the mechanisms together to get the overall reaction. If you can't, then you throw it out. Now, terminology. When we refer to an elementary step, if an elementary step only has one molecule which reacting, and that's not this one, because if we have two of these, that means we had two molecules that had to react with one another. Right? But if we have a single molecule in an elementary step, it's called unimolecular. So it could become, it could change into one product, which is unlikely, but more than likely it would decompose. Unimolecular would decompose into two either products or intermediates. If we have two like this, that's a bimolecular. And this is not an example, but if we had three reactants in a step, remember, we're still talking about elementary steps, and this is termolecular. Okay. If it's unimolecular, then we only have one reactant, and this elementary step is first order. If we have two, then this elementary step is second order. If we have three, then it's third order. Now, I know we didn't talk about third order, but this is true. If you have three reactants that have to come together for a particular elementary step, it's termolecular, and that makes it third order. Okay, now what about probabilities? What's the likelihood that this one can occur? Well, all it needs is sufficient energy to decompose, right? So this is very probable. This one is less probable, but not too bad, where you have to bring two species together in order to get a reaction, and they have to come together with sufficient energy, and they have to be oriented correctly, right, in order for the reaction to go. So that being said, it's a little less likely that a bimolecular will be a step. Termolecular steps are almost impossible, very rare. We only use termoleculars when nothing else will do. Why? Because if a bimolecular has difficulty with enough energy to get the right orientation for the reaction to occur, just think about three molecules have to come together in exactly the right orientation to make the reaction occur in an elementary step. It almost never happens. Very, very rare. Okay. Now, when we've got a proposed mechanism with elementary steps, which one is the rate determining step? The slowest one. The rate of the reaction, the overall rate of the reaction, is determined by the slowest elementary step. Now, I don't know which one of these is the slowest, but let's just say this first one is slow. And this one is, well, let's say it's slower, and this one is slow. So this one's slower than that one, so this is the rate determining step. So if we can assume that the equation for this reaction determines the overall rate. And that's how we can work our way to a proposed overall rate mechanism, rate law based upon this step. Now we have to incorporate the rest of them into the rate law as elementary steps, but this is our starting point, the slowest one. Or we could say this is slow and that's fast, doesn't matter. The slowest one determines the rate. I mentioned this rule earlier. You have proposed elementary steps. The first rule is they all must add up to the overall balanced equation. And second, the mechanism that you propose and the derived rate law from the elementary steps must agree with the experimentally determined rate law. So we can use these elementary steps to derive an overall rate law. It must agree with the experimentally determined rate law. So here we have another one. Let's see, let me erase this. Take a quick look at see where we are. All right. So I've animated this one so I don't have to draw it on the board. This dinitrogen pentoxide decomposes. It's a single reactant decomposing into nitrogen dioxide and oxygen. And the proposed mechanism is a three-step process. The first step takes N2O5 and decomposes it into NO2 and NO3. Then the NO2 reacts with the NO3 to produce NO plus oxygen plus NO2. That's a slow step. That's the rate determining step for this reaction. And then NO3, let's see. Hold on a second. Oh, okay. The rate determining step also says that an NO3 reacts with an NO to make two NO2s. Okay, notice that we've got an NO3 reacting as an intermediate and an NO3 again reacting as an intermediate, but we've only said we produced one of them in that first step. So in order to make these three steps, these three elementary steps equal the stoichiometric reaction, we have to do some modifications. So the first reaction has to be doubled in order to give us two NO3s. Now we can cancel those NO3s because those are intermediates. The two NO3s in the first step now cancel the two NO3s on the reactant side of the step 2 and step 3. Then the NO2s, which happen to be on either side of the second step, they also cancel. And the NOs are intermediates, so they have to cancel. And then we have to add those up. Let's see if we add those up, what do we get? Well, 2N2O5, right? 2 times that, N2O5. And then what about the other side? Well, we have two NO2s from that first elementary step. And then we work our way down. There's an O2. There's an O2. And then the third one has two NO2s also, plus two NO2. So there's our 4 NO2s and oxygen. So the first condition is satisfied with this this mechanism. All right. We have added them together and found that they agree with the overall reaction. Let's see. Oh, we don't have the data to see if the rate law for the overall agrees with the rate law derived from the elementary steps. And so we'll have to work a different problem to get that far. But we satisfied the first step, the first condition. That is, the mechanism steps have to add together to the overall reaction. Balanced equation. Okay. Now we're going to take this proposed reaction, it's the A plus 2B yields C. Yep, C. And this is the proposed step 1 is A plus B yields D. And this is fast. Very fast. So whatever we get here makes D, and then D can go back and forth. So it stabilizes very quickly with some A and B and some D. Then step 2, we take that D and combine it with another B. Right, we got one there. And this is slow. And it produces our C. Oops. There we go. Okay, write the rate law for this reaction. So where would we start? We would start with the slow step. So we would say the rate is equal to, and remember with elementary steps, we can derive the rate expression for this one from the equation. So it's bimolecular. That means there's a K, there's a D to the first power, and a B to the first power. Okay, so that's our starting point. Let's see. Oh, I forgot. Does it meet the first condition? Well, let's see. D's cancel. We're left with two B's, A's, and a C. So yes, the first condition is met. We sum the elementary steps, we get the overall reaction. Okay, now, since this is a fast equilibrium, we have a K going one direction and a K going the other direction. And for this one, we have a K. Let's see, this is a K1, this is K minus 1. This is a K2 going that direction. Because it's slow, it only has one K. It's not fast enough to go back the other direction and influence the reaction mechanism. So now that we know that, we start off with our slow step, which is this one right here. Now notice that this rate law doesn't have, it has a D term in it, right? And the overall reaction doesn't have a D. Plus it doesn't have A in there. So we need to find a way to keep the B and get rid of the D. Oh, by the way, that K2 is here. Okay. Yeah, what's wrong with this picture? D is not a reactant. So we can't keep the reaction, the rate law as it is. Okay. The forward and the reverse reaction rates are equal. So if we write an expression for the forward here, which would be rate equals forward reaction would be K1 for the forward, and then A, and then B, because there's only one of them, right? First order, first order, first order, first order. But that's equal to the reverse reaction rate, which is K minus 1 times D, the first order. Okay. Now we can derive an expression for D and substitute it in here. Right, so this one is equal to that one. So what is D equal to? D is equal to, bring this K over here. 1 over K minus 1 times A. B. There we go. Now we can substitute this in here. Now the rate becomes K2, and then whatever D is, which is K1 over K minus 1 times A, B. And this is times B also, right? So we substituted that in here, kept this one here, kept that one there. Now we just reduce it. Well, these are all constants. K2, K1 divided by K1. We're just going to call all of these together K. And then A to the first power. And then B to the second power. Okay. So now we have a value for D. We're going to substitute it in that expression here. It's all animated. And that's where this overall K is equal to these individual step Ks in a single rate constant. So there's your equation derived from the rate law. Now the question is, with our experimentally determined rate law, is that expression K times A plus B, A times B squared, is that equal to the experimentally determined one? And since this is theoretical, we don't have that data to go by, but it should be. If we accept this rate law, this mechanism, then that rate law should be equal to experimentally determined rate law for that overall equation. Okay? All right. All right. So now, up to this point, we've been talking about laws. And we've not tried to explain anything about reaction rates in terms of why things happen. We sort of alluded to it in terms of unimolecular, bimolecular, and intermolecular reactions, right? Saying, all right, why is one more likely than the other one? But that's as far as we went. The collision model of chemical reactions tries to explain why things happen. And actually, it gives us a way to quantify some aspects of a reaction. First of all, the collision model requires and anytime you see a model, there has to be a theory behind it, right? Models don't occur alone. The model must represent a theory of some kind. So one of the conditions required for this model is that molecules, or atoms for that matter, molecules must collide. If they don't collide, there will be no reaction. Right? That seems simple, right? But you'd be surprised how simple descriptive statements are overlooked sometimes by scientists. So we state that explicitly. Molecules must collide for a reaction to occur. 2, they must have a minimum amount of energy for the reaction to occur. That's equal to E sub A. We call the activation energy. And that, not always, but 2 ways that I can think of right now to ensure that we have that activation energy is the correct temperature. Do we have a high enough temperature to reach that? Because temperature is an expression of the average kinetic energy of all the molecules in a mixture. So if we have a higher temperature, then all the molecules are going to, on average, have a higher kinetic energy, and that supplies the activation energy for the reaction when they collide. The other way is through light. Sometimes we can shine a UV light on a mixture, and that supplies the activation energy. And then 3, we have to have the proper orientation. Orientation of molecules for a reaction to occur. Those are required conditions for the collision model. Okay. Here's the way we draw and express that. I'm going to have to erase some of this, make room. On our graph, we have reaction progress, whatever that means. Usually time. Over time, we see. And this is energy of all the reactants and products together at one time. So if we start off at an energy here, let's say here. We start off here with our reactants. And then there is enough energy supplied so that when they collide, they reach this peak right here. That is the activation energy. And if they have enough energy, and this can be visualized as a single collision. And you can have billions of collisions per second. But for each collision, there must be a minimum energy obtained. And for that reaction, if the collision doesn't have enough energy, right, the average energy, of course, might be a certain level, but some of them might be low and some of them might be high. The ones that are high above that activation energy have the potential to produce a reaction. So if that's the case, then it reaches this transition state. Or sometimes you'll see it called an activated complex. Once it reaches that point, then it can proceed down to products. Okay. Now, in this case, the reactants had more energy than the products do. So where'd that energy go? It was evolved. This is an exothermic reaction. Now, the overall difference here is the enthalpy for that reaction. Okay. All right, so we've got illustrated, let's see, what is that? Nitrogen dioxide produces this activated complex. And in this case, we must have, well, that's not nitrogen dioxide, it's, yeah, they got a bromine in there. Okay. That's not a good. It's got two reds. It needs to have bromine needs to be a different color. Right, so that's not a good representation. Anyway, if you meet this minimum amount of energy for any one collision, you will produce products. Okay. So the reason that you need orientation, correct orientation, is that in most cases you have to, before you can form bonds, you got to break bonds, and you go through an intermediate step, right? Showed up there at the top, where you're starting to form a bond between those two bromines. I think they're calling the ones on the right bromines. And the bonds of the bromines with their molecules are breaking. So those dotted lines mean that you're starting to break some bonds and you're forming new bonds. And if it's not oriented correctly, those bonds cannot form. Or the correct ones can't be broken either. Even if they are broken, you're not going to get the right product. I guess that's an explanation for side reactions, forming products that you don't want. Okay, I've already said that. Now, Arrhenius was I think he was Swedish. I believe he was Swedish. He might be Danish. Scientist who quantified the rate constant with activation energy. And this is his equation. Now, this would be considered the differential equation. It can be modified, and we can derive an integrated equation from this that is more useful. But this also explains the relationship of the K value to the activation energy, right? It's a power of E. E is that base of the natural log. And it's also related to temperature. So activation energy and temperature are related, but they're separate terms in this expression. Now, we don't know what A is. It has to be experimentally determined. It's how often are the reactants colliding, and what's the steric effect? It combines those two terms. And the gas constant is the one that has energy in it, 8.3145. Temperature, of course, has to be in Kelvin, right? That hasn't changed. Now, this equation is the linear format. It's an integrated version. And what we see with this equation is what we have is the ability to plot data from two or more reactions and determine what the activation energy for that reaction is. If we have the natural log of K values equals negative slope of activation energy over R, and 1 over T is our X value, Y equals MX plus the natural log of A, which was that constant we talked about. Then what we need to do is plot the natural log of our K's against 1 over T. And that will help, that allows us to derive the activation energy. This is the linear form of the Arrhenius equation. Oops, back up. So now we just need the change in Y divided by the change in X gives us this value. So the slope of that line is going to be negative, but it's going to be equal to E sub A over R. Well, we know what the slope is. We know what R is. We can solve for activation energy. All right. So this is a problem I thought up. I guess I'll leave that there. If you've ever had any biology courses, this is where I first heard this rule of thumb. Biology courses, the rate of a chemical reaction doubles with every 10-degree increase in temperature. So this says 10K, but 10 degrees Celsius would be the same thing because of the same size unit. But now that we know we have a Arrhenius equation, then we can take that rule of thumb and say, all right, what would the activation energy have to be? What would the value have to be for a chemical reaction for that rule of thumb to be exact, to be true? And we have to restrict our temperatures. So let's say between 25 and 35. We could use any two temperatures, and the value for activation energy would probably change a little bit. But if we know the change in temperature was between 25 and 35, and we wanted the reaction rate to double, right? This value to double, or what would this value have to be for that value? Excuse me, that value would have to be for this statement to be true, right? So we have, and we're going to use Arrhenius' original equation, and that works out pretty well because we're going to ratio the two, right? 25 degrees Celsius would be 298 K and 35 would be 308 K. So what we're saying is, if we go from K1 to K2, the rate must double, which means K2 is equal to 2 times K1. 2 times K1 equals K2. For the rate to double, that would have to be the case. K would have to double in order for the reaction rate to double. So now that we have an expression for each of the Ks, right, the Arrhenius expression for each of the Ks, and the temperature changed, right, temperature changed, then we can ratio those two. And this is where some exponential math comes in, right? What we find is that if E to a power divided by E to another power, then it's the same as E to the numerator power minus the denominator power. And since the denominator is a negative, that becomes a positive. So it's minus E to the A over R T 2 T sub 2 plus activation energy divided R T to the 1. Okay. So now we factor out, we factor out the minus E sub A over R. And that gives us the reciprocal of T2 minus the reciprocal of T1. Now we're going to solve for E sub A because we know what the T values are. So we substitute in the T values right down here, and we substitute in the R value, and we solve for E sub A. And we find that if the activation energy is 52.9 kilojoules for that reaction, then the rule of thumb is valid. In other words, for every 10-degree rise, well, between 25 and 35, then you get a doubling of the reaction rate. All right, so let's talk about catalysts. What does a catalyst do? And I'm going to leave that. Picture there because we're going to superimpose on that what a catalyst does. A catalyst causes the reaction rate to increase. But the catalyst goes in the front end and comes out the back end as a product. And actually, it participates in the reaction, but it's not consumed by the reaction. In fact, it provides an alternate mechanism, an alternate pathway for the reaction, which happens to have a lower activation energy. This is the activation energy for a catalyst. So it provides a different mechanism. Right? So the mechanism that you had for the uncatalyzed reaction is no longer valid. You need a new mechanism that incorporates the catalyst. Okay, that's another way to look at it. In this reaction, the way it's written, the reactants are lower energy than the products. So this is an endothermic reaction. Okay. Now, another way to look at this is look from the collision model, the number of collisions with a given amount of energy, and then the activation energy on the x-axis. So what we're saying is this is the energy of all the reactants, and this is the number or the number of collisions. Okay. So let's say we have a description of the number of collisions versus energy is like that. Kind of looks like a chi-square curve. Anybody that's done biology and has been introduced to statistics in biology knows what a chi-square is. But the number of collisions with sufficient energy to exceed the activation energy, and this is uncatalyzed, is this amount right here. All right. So that determines the reaction rate. The number of collisions that perform a successful reaction are only out here. The rest of these don't have enough energy. The collisions that occur here are insufficient in energy. If we add a catalyst, we actually reduce the activation energy to this point. Catalyzed. Now we add many more collisions that actually produce a reaction. That's why the reaction increases with a catalyst. That's another way of visualizing it. Now, catalysts can occur in different forms, depending on whether the catalyst is the same phase as the reactants or a different phase. If the reactant is a different phase, if the catalyst is a different phase than the reactants, then we call it a heterogeneous catalyst. For instance, let's say, catalytic converter in the exhaust of your car, right? Heterogeneous catalyst. Example would be the ceramic beads or ceramic matrix. I don't think they use beads anymore. Ceramic matrix coated with platinum and palladium. So the exhaust gases, obviously, in the exhaust from your car coming off the engine are gases, but this is a solid, right? So it's a heterogeneous catalyst. And the gases from your exhaust have to adsorb to the surface of that catalyst in order for the catalyst to work. Now, there's a difference between adsorption and absorption. Absorption is like paper towel picking up water, right? The water actually goes into the matrix of the fibers of the paper towel. Whereas adsorption is a surface phenomenon. The gas molecules are attached to the surface of the catalyst and they react at the surface level. That's the difference between adsorption and absorption. And this occurs in several steps that we visualize. The adsorption of your reactants on the surface and followed by their activation. Then they must migrate to one another along the surface of that catalyst and react, and then they desorb, they escape as products. Let's see, do I have an animation? Well, that's a catalytic converter. I remember when catalytic converters first came out, they were essentially just canisters with ceramic beads coated with the platinum and palladium, the catalyst. Ceramic bead was just a matrix to hold them. And shade tree mechanics figured out pretty quick that all you had to do, because catalysts of the catalytic converter presented a back pressure on your engine, and the engine did not run with as much power. It produced fewer pollutants, but it didn't have the same power. So shade tree mechanics would just go into the car and take a screwdriver and pop a hole in the canister, and all the beads would run out. Right? They might run the engine to help push them out, and then just kind of braze over the hole, and now you've got an uncatalyzed engine at the same power it had before. Well, now those catalytic converters are made of a solid matrix of ceramic that's coated with platinum and palladium. So you can't poke a hole and get rid of them anymore. All right. Okay. That's a heterogeneous catalyst. Now we have homogeneous catalysts as a possibility. And that occurs when the catalyst and the reactants are in the same phase. Enzymes are a good example of that. Enzymes are what we call biological catalysts. Now, I'll describe the differences here in a second. Let's see. Oh, I got a video that's gonna, hopefully it'll work, that shows you a homogeneous catalyst decomposing hydrogen peroxide to water and oxygen gas. And so we need, let's see. Let's see, 2 here. One, two here. There we go. That's balanced. Now, this will happen without a catalyst, but it happens very slowly. That's why hydrogen peroxide on your medicine cabinet shelf is good for a certain period of time, but even you will notice in those plastic bottles, they're brown, so the light can't get in there and precipitate a reaction. But even then, the bottle tends to swell over time because the hydrogen peroxide is decomposing very slowly, but it's still decomposing. And if you open the cap, you might hear it go and release some of that gas. But if you add the right catalyst, this reaction will occur very fast. And that's what this, I hope this video will show you.
Can try yours. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay. So
whoa,
we're releasing
okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap. Okay. It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff.
This is like more of a...
So what was happening there was a catalyst was added. In fact, it was the potassium iodide in aqueous solution was dumped into that container, and that is a homogeneous catalyst because it's in the same phase as the hydrogen peroxide. And it caused a rapid release, a rapid decomposition to water and oxygen. Notice the two colors there. One of my students, this was years ago, who's, I don't think they were married at the time, his girlfriend was expecting, and they were having a gender reveal party. So they got a 2-liter bottle, and they put this hydrogen peroxide, and it works best if it's at least 30%. Not 3% is in your medicine cabinet. 30% works better. And he dumped some dishwashing liquid in there, and then some food coloring for the gender, like blue for boy and red for girl. And that's how they reveal the gender. Unfortunately, ultrasound later showed that they revealed the wrong gender, so they had to do it all over again. But that's a homogeneous catalyst, and it requires a different mechanism. And in fact, the mechanism for this has been determined to be extremely complex. I think it's 5 or 6 steps in the elementary steps. Well, maybe 4. So that's what's happening in this reaction. And the rate determining step is that first one, where the iodide ion combines with the hydrogen peroxide to make that HOI and OH minus. Everything after that happens really fast. So even this is, don't misunderstand, that slow step is orders of magnitude faster than the uncatalyzed reaction. Right? But it is the rate determining step. And notice that if you see a list of mechanisms and you see something in the mechanism, say a first one or anyone down the line has a species that goes in and comes out at the end, that's a catalyst. Whereas if you have a reaction and produce something as a product in an intermediate step, and then it's consumed in a subsequent step, that's an intermediate. There's a difference between that and the catalyst. Catalyst comes in and goes out. Intermediates are created inside and disappear before you produce products. Okay. Here's another example of a homogeneous catalyst. I think these are all gases. Yeah. So in this case, this is a bad catalyst because what we want in our upper atmosphere is ozone. Ozone is a very effective absorber of ultraviolet radiation. So it protects us on the Earth's surface from UV rays coming from the sun. But if we produce nitrogen monoxide in sufficient quantities, eventually it drifts its way up to the upper atmosphere and decomposes ozone. Makes it go back to oxygen. And the production of ozone can't keep up with it. So we have what's been discovered as ozone holes, especially at the poles in our upper atmosphere. The same kind of effect can be produced by chlorofluorocarbons or freons. The original freon was, and there's a naming, a nomenclature for these refrigerants. Freon 12 is actually methane substituted with 2 chlorines and 2 fluorines. But the sunlight causes a partial decomposition of the Freon 12, and it produces this catalyst. The chlorine, right? Chlorine is going to have, right, 7 valence electrons, which means what? Elemental chlorine is a, and the word just flew right out of my head, is a free radical, excuse me, is a free radical. In order to have a free radical, you need at least one unpaired electron. And that's what atomic chlorine is. It's very, very reactive. And it causes ozone decomposition. Okay. That's all for the introductory lecture for chapter 12.